session 2. And okay, over to you, Jyoti.
So Tanay, can you start the recording as well, maybe, or?
Yeah, 1 second. I'm just setting up the
session
YouTube.
2.
Yeah, we are live. So let me just. Yeah, you're recording also.
All right. Welcome to this second session of the first day of this conference. So our first speaker is Professor Jerome Gauntlett from the Imperial College London, and he will be talking about spatially modulated and supersymmetric mass deformations of n=4 super Yang-Mills. Professor Gauntlett, please start.
Good, thank you. Thank you for the introduction. And I'd like to thank the organizers, Tanay, Suresh, and Ayan, for putting on this conference and for the opportunity to speak. It's actually the last time I was in India was in the mid-90s, and ever since then I've been meaning to go all the time. And when this invitation came up, it was like, well, this is definitely happening. And then of course the crisis kicked off, so it's a sad that I can't be there. In particular, I would have definitely gone and seen a Chennai Super Kings cricket match, which would have been a lot of fun. So I want to talk about some work I've been doing over the last 6 months. And this is with these collaborators down here. Hopefully you can see my mouse moving. Egal Arav, who was a postdoc at Imperial and has just moved to Amsterdam. My student, Matthew Chung, who's at Imperial. Matt Roberts, who's a postdoc at Imperial. And Chris Rosen, who was also a postdoc at Imperial and now is in Barcelona. And the work's based on these two papers down here. Now, I know that in this world of Zoom meetings and so on, everyone's attention span is incredibly short, and the temptation to do something else is very great. So I'm going to give you an elevator pitch for this talk, and the elevator pitch is following. So I want to take or consider n=4 supersymmetric Yang-Mills theory. And then I want to deform it by some mass operators, which could be both fermionic masses and bosonic masses. And I'll allow those masses to depend on the spatial coordinates. And the questions I'm interested in are, can we preserve supersymmetry? So if we allow M, we certainly can, we know that we can preserve supersymmetry if we have homogeneous mass deformation, so if M is a constant, under certain restrictions. But if the mass depends on spatial coordinates, is it possible? The answer is going to be yes. If we allow the spatial dependence just depend on one spatial dimension. A second question I'll be interested in is, can we preserve superconformal supersymmetry? So in particular, can we preserve conformal invariance? So with masses, one's first thought is no, that's not going to be possible. But if we allow the mass to just depend on one spatial dimension, we can ask for preservation of conformal invariance in the interface, the codimension 1 interface. And we'll see, yes, you can preserve conformal symmetry and moreover, superconformal symmetry. And finally, can we study this holographically? So the answer to that is certainly yes. We know how to study n=4 Yang-Mills theory and its deformations by constructing solutions of type 2p supergravity. And so we will do so. And we'll realize some of the constructions that I just alluded to in the previous 2 points. But highly surprisingly, we also got some new solutions which we didn't expect at all. Okay, so if that doesn't whet your appetite, go away, make yourself a cup of tea or whatever else you like to do. You can, behind your Zoom hidden screen. But if you're interested, let's press on. And let me then begin with a more leisurely introduction. So I just want to put some of these questions in a slightly broader context. So let's just think about a general conformal field theory and deform it by some operators with some spatially dependent couplings. And the operators here I'm imagining could be relevant operators, as in the mass operators I was just thinking about, or they could be marginal operators as well. And when these deformations are homogeneous, so these couplings lambda independent of the spatial coordinates, we know that will induce a renormalization group flow from the CFT, and we would then flow into the infrared and realize some interesting dynamics depending on the deformation of the CFT we started from. So for example, we could start with one CFT in the UV and then flow to another CFT in the IR. And of course, we can flow to other dynamics in the infrared, confining, and so on. When the couplings are dependent on the coordinates, spatial coordinates, and we have our other operators, there's a different kind of renormalization group flow that we termed boomerang RG flows, where you start with some CFT in the UV, then you deform it, and then you come back to exactly the same CFT in the IR. So that's why we call them boomerang flows. And this doesn't violate any C theorems or anything like that, because we have broken the translation variance. So that's a necessary part of these RG flows. Furthermore, these flows can be supersymmetric, and although I won't be going into it today, they can also have some intermediate scaling behavior. So as you start propagating around on your RG flow at some intermediate area, you can approach some other fixed points of RG flow, and that can dominate the scaling for some extended period of scales on your RG flow. When the couplings are depending on the spatial coordinates, a very well-studied framework is that of Janus configurations, when one preserves conformal invariance on a codimension 1 interface. So if we think about 4-dimensional CFTs, we can imagine that we have a CFT on one side, for example, with a dimensionless coupling constant G1. We have a 3-dimensional interface. We have another CFT with another coupling constant G2 on the other side. And we preserve conformal invariance on this interface. So the first constructions of this was by Back, oops, that's a typo, I'm sorry, Michael. Back, Gutperl, and Haranu. And they considered n equals 4 Yang-Mills theory, and they allowed for a varying coupling constant in one dimension. And when you had a step function, then they argued that that was conformally invariant. You can generalize this away from just having the coupling constant depending on a spatial coordinate. You can also have the dimensionless coupling constant tau, which also includes the theta angle depending on the spatial coordinate. And you can preserve conformal invariance. And as many of you will know, this is actually an extremely well-studied subject. Many people have worked on this, and you can have these varying tau couplings, and you can preserve various amounts of supersymmetry. And I've just listed a few of the people who have worked on this topic. So here, one of the novel features is that we will have Janus configurations that have a constant tau. So Janus configuration of n equals 4 Yang-Mills theory, but that tau is constant. Another thing one might think about is RG interfaces. So let's imagine we have some RG flow driven by a relevant operator in the homogeneous setting. So we go from one CFT to another CFT. Then you can imagine in your mind's eye that we have an interface between the two CFTs, so different from the Janus, and then we have different CFTs on either side, and we preserve conformal invariance on the interface. Actually, it's not immediately clear how you might do this. So what you might like to do is you have CFT1 on this side, CFT1 on this side, and then you deform just this half plane by the operator which induces the flow, and then hope that you can realize this configuration. But of course, once you do that deformation, it's not completely clear that you can just, because you're breaking the translation invariance, and it's a little bit unclear what the rules are to allow yourself to get an RG flow that you would end up with that interface. Nevertheless, here we will construct, in the context of holography, RG interfaces of n equals 4 Yang-Mills theory with n equals 4 on one side, another CFT on the other side, exactly of this form. And the final motivation is actually one that I won't be discussing anymore in this talk, but I just wanted to mention it because this is how I started thinking about these topics. And it's in the context of applied ADS CFT. So as we'll hear about in other talks in this meeting, one considers a planar CFT, and you might get finite temperature, and you might have some various deformations, chemical potentials, and so on. And a basic observable in this framework of trying to make connections with condensed matter, for example, is to analyze thermoelectric DC conductivity. But if the CFT preserves translations, momentum is conserved, and the DC response is infinite. So this was a problem that was several years ago confronted, and it was realized that at least one way to confront this in a natural way is to invoke a mechanism to explicitly break the translations. And you can do this by having some operators, relevant operators, that have some spatially dependent couplings. And in that context, it's natural to take those couplings to be periodic, and then we call this a holographic lattice. So there's been an enormous amount of work on holographic lattices in the context of applied ADS CFT. And just to give you a very brief flavor of some interesting things that come out there, one is that these lead to interesting novel ground states in the infrared, conventional metals, novel metals, insulators, and there's been a lot of work in that direction. And it's also been a framework where there's interesting results about black hole physics connected to these observables. In particular, as quite a universal result in the context of ADS CFT, you can obtain the DC conductivity purely by calculating quantities on the black hole horizon, in particular solving the Navier-Stokes equations on the black hole horizon. So that's a nice formal result that came out of thinking about these spatially modulated deformations, formal and with practical implications. Okay, so let me then move to talk about n equals 4. So what I specifically want to do is think about the n equals 1 star deformations of n equals 4. So recall that we can, n equals 4 Yang-Mills theory has an SO6 R symmetry. But we can view n equals 4 as an n equals 1 theory, and that's then a vector multiplet coupled to 3 chiral multiplets, which I'll call capital phi A. And the n equals 4 then in this language just has a superpotential, which I've given by this expression here. And this formalism keeps manifest just a subgroup SU3 of the R symmetry of the full SU4. And the n equals 1 star deformations, when you deform the theory by adding in this deformed superpotential here, so these mass terms for the chirals. And again, many people have worked on this, starting with Nagy and Witten and Rory, Polchinski, Strassler, many people have been working on this, and there's lots of interesting things to say. So these MIA are constant and complex mass parameters. And what are we interested, well, what we focused on was 3 cases, the 1 mass model, the equal mass model, and the n equals 2 star model. And these have different set of masses which are appearing in this deformed superpotential. So the 1 mass model just has M3 non-zero, has an SU2 cross U1 R symmetry. And let me remind you that this is particularly interesting because this is a model where that homogeneous mass deformation flows to the Lee-Strassler fixed point. The Lee-Strassler is an n equals 1 interacting, strongly coupled interacting conformal field theory, and it lies inside this 1 mass model. We'll also consider the equal mass model for obvious reasons, M1 equals M2 equals M3. This is called the equal mass model. And this was studied by GPPZ, Polchinski and Strassler, and many other people. And this is associated, these deformations, with a very intricate vacuum structure. As a model with M3 equals 0 and M1, you actually preserve n equals 2 super. So the basic thing to analyze is these n=1 star deformations and allowing the masses to depend on the one spatial dimension. Actually, I just got a signal saying it's unstable. Can you still hear me clearly?
Yes, we can hear you clearly. Please go ahead.
Okay, great, thank you. Good, so that's what we want to do. So the plan then is I'll break the rest of the talk into a field theory part. How do you deform these n=1 theories with spatially dependent masses, allowing for supersymmetry? And we can answer this by using the formalism of Festuccia and Seiberg. And then the second part of the talk is going to be on holography, constructing solutions of type 2b supergravity. And there's three broad class of solutions that I want to present to you. The first is, as I mentioned before, is a Janus solution, which has constant tau, coupling constant n=4. So it has n=4 on one side and n=4 on the other side. And another one, which a priori I wasn't clear you could have it, is the Lee-Strassler conformal field theory on one side and Lee-Strassler conformal field theory on the other side. We'll also find another class of solutions, which has n=4 on one side of the interface and the Lee-Strassler fixed point on the other side. So by definition, that's an RG interface solution. And quite surprisingly, in just playing around with these BPS equations for the supergravity, we came across a very interesting solution, which is ADS4 cross S1 cross S5. So I'll explain that as well. So let me start with the field theory. So we're interested in supersymmetric deformations of n=4 in general. And what Festuccia and Seiberg say is you should take your theory, couple to an off-shell conformal supergravity, in this case n=4, and then you take a limit where you all the supergravity fields become non-dynamical. Take the Planck mass to infinity. So this problem was actually first looked at by Travis Maxfield, and it was actually just a small extension of these beautiful old works of people who worked very hard over 30 years ago on supergravity, who looked at conformal supergravity and coupling of n=4 to conformal supergravity. So let me just outline what the final result is of going through that procedure. The first point is that the couplings you can consider, coupling n=4 Yang-Mills theory, consist of the n=4 superconformal current multiplet. And in terms of the R-symmetry representations, they transform in these SU4 representations here. So we have a singlet metric. And for our purposes, I'm going to take that to be always flat space. There's a singlet which is tau. And I'll take that to be constant. There's currents in the 15, the adjoint of SU4, which I'll set to 0. There's also a 2 form in the 6 representation, which I'll set to 0. But what I'll focus on is these guys. There's E's, which we'll see are fermion masses in the 10 of SU4. And there's also these D's, which are related to boson masses, which are in the 20 prime of SU4. And specifically, we want to allow them to depend on a spatial coordinate, y. So here is n=4 Yang-Mills theory. And on the first two lines, this is a bit of a messy equation. It's actually what you know and love. It's the kinetic term for the gauge field, the theta term, kinetic term for the scalars, which I've just written in terms of SU4 notation here. So these are 6 scalars. Here's the kinetic term for the fermions. And here's the rest of the couplings that go up the Yukawas and so on that make up the n=4 Yang-Mills theory. And the deformations I'm talking about going through that procedure consist of, the masses for the bosons here, the masses for the fermions here, and some extra cubic couplings. And the masses for the fermions, as I said, are just given by the EIJ. And the masses for the bosons, which are appearing here, are given by the Ds, as well as a quadratic correction with the, depending on the Es. So you can add these couplings, and the question is, can that be supersymmetric? And if you go through this procedure, you find that the conditions for supersymmetry, given the conditions I've imposed, are given by these three equations here. So let's solve them, and we can solve them as follows. So we first look at the first equation, and we see that this preserved supersymmetries, the epsilon j, and there's 4 of them, it's in the 4 of SU4, should be a null vector of the matrix E. So if for n equals 1 star theories, we consider fermion masses like this, which is exactly in this language what I was talking about before, then clearly if we take epsilon to be that vector there, that's going to be a null vector and it solves those equations. The last equation is clearly solved if epsilon 4 is constant. So the business is really to solve this equation. And you see you have a d slash E term here, you have a d times E term, and you have these E squared terms that are appearing here. And it's actually straightforward to solve this. The only thing, and you solve it by noticing that with one gamma matrix here, it's possible to impose a projection on the chiral spinor epsilon 4, as I've indicated there. So epsilon 4 is chiral and epsilon downstairs 4 is antichiral, provided that the masses just depend on one spatial dimension. And the one spatial dimension is simply just because we have this d slash term here. So you can use gamma y as a projection condition. And then, well, I'm not going to write out all the indices. The structure then of solving that equation with these projection is just that d is basically m squared plus the spatial derivative of m with respect to y. In other words, the boson masses are completely fixed by the fermion masses. That's the key point. Key point, boson masses fixed by the fermion masses, and you can preserve supersymmetry if the masses, the fermion masses, just depend on one spatial dimension. How about conformal invariance? Well, I won't write down the conditions, but there's a similar analysis you just go through. And when the dust settles, if you take the masses to be 1 on y, so if you think of dimension m is 1, dimension of 1 on y is 1. So the lambdas are dimensionless. So this looks plausible to be conformally invariant, superconformally invariant, and it is. Obviously, this is singular when y goes to 0. So we can imagine having n equals 4 on one side with these masses 1 on y on this side. And on the other side, we have n equals 4 Yang-Mills theory with a different set of coupling constants on the other side. And these are, from a field theory point of view, precisely the Janus configurations with constant tau that I was mentioning. So it's going through this Festuccia-Seiberg formalism that you immediately see that this is a possibility that has been overlooked for well, until now. Okay, so now let me switch to holography. So we want to construct supergravity solutions that are dual to these deformations I was just describing. So we want to construct solutions of type 2p supergravity. And since we're looking at n equals 4, it's extremely convenient to focus on d equals 5 SO6 maximal gauge supergravity. So recall, this theory arises as a consistent truncation of type 2b on the 5 sphere. So you start with 2b and d equals 10, do a Kaluza-Klein reduction on the 5 sphere, and in general, you get an infinite number of fields in 5 dimensions. But the consistent truncation is you throw away an infinite tower, leaving you just the fields of this SO6 gauge supergravity. And it's consistent in the sense that throwing away those infinite fields is consistent, but in that they're not sourced by the other fields. To paraphrase, again, if you have any solution of the SO6 gauge supergravity, you can uplift it to get an exact solution of type 2b. And you can use the formalism of these people here. So that's a massive simplification in constructing solutions of type 2b. It doesn't give you everything, of course, but it gives you a lot and in a much simpler context. It's still complicated. This theory has 42 scalars, which parameterizes this coset here. So one certainly looks for further simplifications. And these people, Bobav et al., had constructed or demonstrated that there's a further truncation to a theory with a metric and 10 scalars, which is exactly what we need for this problem. And it was also very closely connected for the calculations that these people did. So that 10 scalar model has these 10 scalars here. So there's var phi, there's 4 phi scalars. This is a different phi to what I used in field theory. So you can forget the notation from the field theory here for a moment. There's 3 alphas and there's 2 betas. They're all real, so that's 10 scalar fields. So what do they dual to in n equals 4? Well, if we imagine that we write the 3 chiral superfields of n equals 4 as some bosonic fields Zi and some fermions chi, what we have is the following. Var phi is dual to the n equals 4 coupling constant. The phi I are the fermion masses for the 3 chirals. Phi 4 is a gaugino mass. So the phi i's are the fermionic masses that I was mostly interested in, what I call the E's, Eij before. And then alpha and beta 1 and beta 2 are all bosonic masses, quadratic in the Z's. So this has all the operators, or all the fields dual to the operators that we're interested in for looking at deformations of n equals 4. So I'm not going to go into any detail, but the truncation leads to a Lagrangian, which is just an Einstein-Hilbert term, a kinetic term for the real scalars beta 1 and beta 2. And the rest of the fields, the rest of the 8 scalar fields, are packaged together in 4 copies of the hyperbolic disk. So Za, capital A, runs from 1 to 4. It's a function of these 8 scalar fields, and the details aren't important. It's just that they do parameterize 4 copies of this hyperbolic disk here. So this is perfect for looking for solutions of n equals 4 deformed by real mass deformations. So this is the general framework, which is good to think about. For the specific cases I'll talk about in this talk, there's actually further truncations which are convenient. Very briefly, I'm just going to rush over this briefly. The first thing is we can consider an ansatz for this theory which preserves iso 2-1. So the masses just depend on one spatial direction, which I'll call Y3. You can derive BPS equations. Now the BPS equations that describe everything I was talking about before when you don't preserve conformal invariance. But it necessarily involves solving PDEs. So I'm not going to say anything more about this problem except maybe right at the end. The second point, before I continue, is just to briefly mention holographic renormalization. Holographic renormalization is complicated for this theory. There's a lot of finite counter terms involved. But nevertheless, one can make some progress in that direction. And I just want to highlight very briefly some interesting feature that arises when you go through this procedure concerning the conformal anomaly. So the trace of the stress tensor plus these conditions. So this is the expectation value of the operator dual to phi I. Phi I is the source for that operator. And here's the expectation for value for the operator dual to alpha. Here's the source for that operator, and so on. So the general conformal anomaly can be written like this, where on the right-hand side, by definition, it is the anomaly. And I just want to highlight that the anomaly has the usual curvature pieces. It has couplings of the scalars that are conformally invariant, which one might have expected. And there's also these terms that are quadratic in the sources. So it's just very schematic. But the point, a consequence of these is that under a Weyl transformation of the deformed theory, when you deform the boundary metric, is that while the sources would transform homogeneously or covariantly, the expectation values don't transform covariantly. And that's just something you have to live with this anomaly. Okay, so let me continue on. Neither of those points will play any role in the rest of what I want to say. So let's focus now on the Janus configuration. So these are going to be gravity solutions that describe configurations that also preserve conformal invariance. So that's SO32, conformal invariance on the interface. So we write down this metric ansatz here. So ADS4 has these isometries. That's why I've written that down. And AJ is just a function of the radial coordinate. And similarly, all the scalars, the 10 scalar fields, are also functions of the R. And now you put that into the BPS equations of the supergravity theory, and you now get a series of ordinary differential equations. And these are the ordinary differential equations which we can solve, and we have solved, and I'll tell you about them. But before I do this, if you haven't seen these Janus configurations before, there's an important point about these coordinates which may not, that's definitely worth understanding before we go on. So here I've drawn a Pfefferman-Graham coordinate Z, and this is the boundary of the bulk. And I've just put one of the spatial directions here, which is Y3. So that's the standard way you think about holography. There's a Pfefferman-Graham coordinate, you go to the boundary, and then you see the spatial direction Y, and we're interested in things that depend spatially on Y on the boundary. But these coordinates are not those coordinates. Let's in particular look at ADS5, which is a special example of that lies in this ansatz, and I've written it out here. So e to the 2aj is just cosh squared r. Here is the metric on ADS4, and there's the same radial coordinate. And you can do a coordinate transformation to the standard Pfefferman-Graham with Poincare slicing. And the relationship between these coordinates is it's sort of like polar coordinates. So the radial coordinate is going from plus infinity over here, one half line, to minus infinity, the other half line. So the boundary, r goes to plus infinity, is half of the boundary, conformal boundary. R goes to minus infinity is the other half. And they're joined at this point here, where r is finite, and x, the Poincare coordinate, goes to 0. So that's n equals 4. When we're looking at deformations of n equals 4 and solving those ODEs, we want to basically put boundary conditions on one side of the interface, say at r is plus infinity, the first order ordinary differential equations. That gives you a solution in the bulk, and then you can read off what the sources are on the other side, as well as the expectation values. Okay, so they're simple coordinates, but if you haven't seen them before, it gets a little bit confusing. When I say r goes to infinity, you might naively think that's the full boundary, but it's only half of the boundary. Good. So let's have a look at the n equals 1 star models with one mass. So the 10 scalar model can be reduced to a model with 3 scalars. So one complex Z, which depends on phi3 and alpha3, a fermion mass, a boson mass, and one of the betas, another boson mass. So phi3 is dimension 3, and these alphas and betas are dual to operators with dimension 2. The ADS5 vacuum has all the scalars equal to 0. There's also another vacuum of this theory, and it's the least dual to the least Ressler fixed point, and Z1 and beta1 are given by these explicit values which don't matter. The only thing that's important here is there's a plus and minus. So this supergravity framework has 2 ADS5 solutions, both dual to exactly the same least Ressler theory. There's not least Ressler conformal field theory number 1, least Ressler conformal field theory number 2. It's exactly the same conformal field theory, but it's realized in 2 different ways in the supergravity. Okay, good, that's all known. as I was just saying before, we want to solve the BPS equations by, starting on, as r goes to plus infinity, which in the other coordinates is starting on 1/2 plane, imposing some sources for the fields on this side, and then integrating to get the full bulk solution. And then you can deduce both the expectation values of operators on this side, as well as source and expectation values on the other side. So I've just written here, at r goes to infinity, we demand we're going to the n equals 4 vacuum with some sources switched on. These sources aren't all independent. And this now ties back to the field theory thing I said several slides ago, is the fermion masses fix the boson masses in the context of the supergravity. Phi 3s, the source for the fermion masses, is actually fixing what those sources are. So if you know what phi 3s is, you know what all the sources are. So let me now tell you about the solutions. So here is the important results. So there's a 2-parameter family of solutions. And one parameter can be thought of as the angle of the phase of the complex field at the turning point of the function A. It doesn't matter anything more than that, just to say there's another parameter to specify these solutions. So here is a 1-parameter family of solutions specified by the different curves, and they all have a turning point on the real axis. So the blue curves are the n equals 4 Janus solutions. The n equals 4 point at the origin. So this is a parametric plot in the Z1 space. So it's imaginary real part of Z. So the origin is the n equals 4 fixed point. So the solutions in field space start at n equals 4 on one side of the boundary. They go round, and when they get back to the other side of the boundary, they're back at n equals 4. So each blue curve, and they fill up this region in here, corresponds to the n equals 4 Janus solutions labeled by a fermion mass source and constant coupling tau. So that was nice, and we sort of expected that. But now some of the bonus things come in. As you take that source to infinity, you may have thought you just ran off to some singular behavior, but no, you find that the solutions reveal this new solution that starts off at the 2 red dots, which are the 2 fixed points corresponding to the least stress of the solution. So there's the solution which starts at LS minus on one side of the interface and goes to LS plus at the other side. It arises as a limiting class of the Janus solutions. So it's not an n equals 4 Janus solutions, it's a least stress Janus solution. So that was a nice thing. And interestingly, unlike the n equals 4 Januses, this least stress Janus has vanishing sources away from the interface. That's an interesting fact, number 1. Interesting fact number 2 is it's the same CFT on each side of the Janus. Okay, so we can also consider other solutions where the phase is at a different angle. So this was when it was all pi on 2. I should say the black curves are singular at either end. They run off to singularities. So we don't know what their proper interpretation is. This is well known in the Janus story. These singular solutions occur. And let me just not discuss them anymore, because let's discuss the things that we definitely understand and are definitely interesting. So you can ignore the black curves for the moment. Here is a set of solutions when the phase is sitting at some different angle, about 45 degrees. And again, we find something different again. The blue curves start off at n equals 4 on one side of the interface. And in field space, we move around, and when we get back to n equals 4. So we again have a 1-parameter family of Janus solutions of n equals 4. But the limiting solution at some critical value of the n equals 4 source starts off at the n equals 4 vacuum and then ends up at the least stressor vacuum. So that's an interface with n equals 4 on one side and least stressor on the other side, and that's the RG interface. The fact that LS plus is picked out here is simply the fact that I'm ignoring a Z2 flip of solutions where you end up at the LS minus. There's nothing special about LS plus here. So let's just consider these a little bit more. Let's consider the family of those red curves for different turning points. So this is a plot of all the RG interface solutions. So the RG interface starting at the n equals 4 vacuum and then ending at the LS plus vacuum. And I've just drawn them all. And the limiting curve of that family of solutions is the Lee-Strasser Janus solution. And I just wanted to highlight one thing about putting them this way is this dotted line is an interface with n equals 4 on one side, Lee-Strasser on the other side, and vanishing sources on both sides. It's a source-free solution. So that's interesting. Good. Well, I'm nearly done. I wanted to briefly talk about the n equals 1 mass model. It's more complicated because the 10-scalar model has to be reduced to 4 scalars. So we keep fermion masses, including the gauge-ino now, 5-4, boson masses, and also the coupling constant phi joule, sorry, the phi joule to the coupling constant of n equals 4 Yang-Mills theory. However, I don't want to switch these on to sources. So we always take the gauge-ino mass and the coupling constant to have vanishing sources or trivial sources. So we're still looking at fermion masses and boson masses just depending on one spatial dimension. There's now a 4-parameter family of solutions, and we haven't got to the bottom of it all, but I wanted to emphasize one very striking solution. So this is a plot now, plots of just in the Z1, the parametric plots in the Z1, complex Z1 plane. There's another plot for the Z2, which I won't present. And the blue curves, once again, are Janus solutions, starting at n equals 4 at the origin and ending back. But when we started mapping this out, you suddenly see that these little loops start appearing, loop the loops, and the limiting solution is this kind of red curve. And when you blow it up, what you find is all these Janus solutions look like this. So this is AJ, the warp factor. So we're starting at n equals 4 on one side of the interface. We go inside, there's some oscillation, and then we go back to n equals 4. But as we go along these plots, what's happening is more and more of this periodic region is developing. And as you approach this limiting red curve, this periodic configuration extends out to infinity. And that's the new periodic ADS4 cross S1 cross S5 solution of type 2b. It's a fundamental new solution, supersymmetric, and we don't, it's very interesting to understand that further. So just to wrap up then, final comments in the last couple of minutes. What have I done? So from the field theory point of view, by looking at this Festuccia-Seiberg formulas, we know exactly the conditions to see how you can deform n equals 4 preserving supersymmetry. And we're allowing, we saw that we cannot have spatially varying masses for both the bosons and fermions. It's natural to think about what about adding in more deformations? What else is possible? So there's obviously been a lot of work done on adding in curve metrics and background gauge fields, topological twist, for example, preserving supersymmetry. So maybe one can combine the two things together. And as of course, varying tau has also been well studied in the Janus configurations. So I think there's more to be understood just from the field theory by playing around with these equations. From holography, what emerges is a rich class of Janus solutions of n equals 4 theory, a new Janus solutions of the Lee-Strasser fixed point where you have the same CFT on either side of the interface. There's 0 sources on either side. So you think, well, what's holding this together? And that's a good question. All of our analysis doesn't look at the interface itself, for reasons I can explain later. So it's a little bit unclear. And it's also interesting that it's the same CFT on either side, but that's sort of related by some Z2 automorphism. There's an RG interface between n equals 4 and the least Strassler fixed point. And the way in which that construction works probably should generalize in many other cases in holography. Whenever you have a homogeneous flow between two fixed points, you should be able to construct, I believe, some kind of RG interface solution. And finally, there's this novel and completely surprising new ADS4 solution, which needs further study. And final slide, I was focused on talking about the solutions that preserve SO32, but I very briefly mentioned the solutions where you don't have conformal invariance. You just have something depending on the spatial direction, but you don't demand conformal invariance. And I think this is very interesting for further study, but it's not as accessible because you need to solve PDEs. But just to give you a flavor of why I think there's probably a rich set of solutions, is there's an analog of the story I've been talking about in ABGM theory. Kim and Kwon looked at supersymmetric mass deformations of ABGM theory. And then in some previous work, the same people who I've been working with for the things I've been discussing in this talk, we looked at D equals 11 supergravity solutions that were dual to those configurations. And in a certain context, we were able to reduce that whole problem to solving an auxiliary Helmholtz linear PDE equation in the plane. So it's a little bit like LLM or something like that. You have this complicated supergravity solution, supergravity ansatz, but you follow it through and then you end up with a very simple auxiliary problem to solve. And in that context, there was interesting Janus solutions, boomerang RG flows, and so on. So in the context n equals 4, although these PDEs look a bit formidable at the moment, there may be ways of getting access to those and an interesting, more general class of solutions. And I'll stop there.
Thank you, Professor Gauntlett, for a wonderful and very clear talk. So are there any questions or comments?
I have a question.
Yes, please.
Jerome, are the bulk solutions singular or regular at the place of the interface?
Yes, that's a good question. So the bottom line is we don't know. There is almost certainly some singularity there, but the nature of the singularity is very delicate. So there could be distributional sources there in the boundary theory. So if you have the n equals 4 on one side and n equals 4 on the other side, it's possible that there's some hidden distributional sources. Essentially what you need to do is in those coordinates I was describing where you have the boundary and you have the Pfefferman-Graham coordinate, you have to, and the coordinates we're using it is R and X coordinates, you have to zoom in a very careful way to see what's going on with that bit of the boundary. So that's definitely an important technical open issue that we haven't got to the bottom of. That being said, it's a little bit hard, for example, to imagine in the n equals 4 theory and the least Strassler RG interface to imagine that there is a delta function singularity sitting, because what operator is it connected with? Also, the operators in the least Strassler side that are active in this story have a rational scaling dimension. So if you were going to have a delta function with conformal invariance, there's some funny, I mean, it's a funny class of distributional sources you'll have to be considering. So it's a very good question. We don't know the answer to it. Yeah, and I think it's worth thinking about.
Are the curvature invariants regular or singular?
Everything's regular. Everything's actually finite in the bulk. And on the boundary, we have the boundary metric is flat. So everything's well defined, except that in the way in which we constructed the solutions, we have one half plane y greater than 0, y3 greater than 0, another half plane y3 less than 0, and then there's that plane. And the coordinates we've looked at, everywhere in the bulk, right up until that plane at the boundary, is perfectly regular. But exactly how you get there and see a distributional source is unclear. In this Helmholtz case I was mentioning at the end, that was one of the that's a useful reference point, because things were in much better control, and we could also think of the theories with conformal invariance as a limit of the theories without conformal invariance. We could zoom in and actually get a proper handle on these distributional sources. So this issue about of just doing PDEs for the sake of it could actually be very important on it from a technical point of view as well.
Thank you.
Okay, other questions or comments? So, let me ask, one small thing. So, can we, very easily generalize these solutions to finite temperature, for instance, or do you see any, can you put in a black hole in the bulk? Or
yeah, I think absolutely yes. In general, when you start putting in, if you want a black hole, you're going to be necessarily led to PDEs again. So from a conceptual point of view, if we backtrack to that motivation from applied ADS-CFT, that was when one was thinking about, for example, the simplest thing that people looked at was like a varying chemical potential.
Right.
And then you say, what does that look like at finite temperature? And then there was that spatial direction gets involved as well as the radial direction, and one solves PDEs. So in this context, with these spatial fermionic and bosonic mass deformations, one can certainly ask that question. But it might be, well, it's difficult in the sense that one has to confront those PDEs again, which I don't think is, when people say PDEs, some people just tune off and say, well, I'm not interested anymore. I mean, I think that's not the right attitude. I mean, I don't think that it's that difficult a problem. And as a big community, we have lots of people who are expert at this. And I think it's finding the right sort of problems and questions to look at. And I think in this framework, they are interesting problems to look at.
All right. Okay, other questions and comments?
Well, I have a naive question.
Yes, please.
So with this space-time dependence of the masses, it looks like the propagators effectively become ADS propagators. And does this have any interpretation?
First, hi, Charlotte.
Hi.
So you were saying that they become ADS5 propagators?
Or ADS4? Or,
yeah. So I mean, the short answer is I don't know. Once you have these solutions, you could then, in principle, calculate higher, correlation functions for these backgrounds. So all that we did was just look at the one-point functions. But if you wanted to calculate higher order correlation functions, certainly, since you preserve the SO3 to invariance, that the structure of those propagators would be there, and one could carry out those calculations, but one would have to work harder. And it's probably.
So what it means that the defect acts like some kind of ADS boundary, right?
Except, yes, exactly what sort of boundary it is I think is sort of an open issue.
Yes.
I mean, what can actually go through that boundary from a boundary point of view? From the bulk point of view, in principle, this could be addressed, but it might be nice to understand it better just purely from the field theory point of view too.
Yes. No, I also wanted to ask Elias, what is the field theory on the boundary? But you cannot say much more than what you already did.
I don't know what the answer is.
Okay.
I think it's interesting.
But you have somehow to rescale the fields to define them in a good way on the boundary, or how should I understand it?
I'm not sure technically what the best way to do that is. I mean, you still away from the interface. You still have all the operators, obviously, of n equals 4 Young-Mills theory.
Yes.
But in terms of yeah, setting up the problem so that you make that manifest. I mean, I suppose maybe you need to dress up the operators with appropriate powers of the that transverse direction. Yeah, I think that's right.
Okay, thank you.
All right. So we can thank Professor Gauntlett once more for a very beautiful talk. And so let us go on to our next speaker for this session. So Professor Kiritsis, can you share your slides?
Just a minute. Okay. Can you see them?
Yes, we can see them very clearly.
Let me.
Yeah, maybe you can full screen. Yes.
Yeah. Okay.
Okay, so our next speaker for this session is Professor Elias Kiritsis, and he will be talking about emergent gravity from hidden sectors and TT deformations. Professor Kiritsis, please start your talk.
Thank you very much. Good morning, good afternoon, depending on the place. The work I would like to present to you today is based on a recent paper we published with Panagiotis Begios and Vasilis Niarchos, some ongoing work, and also is based on some earlier work in the recent past. As you all know, all fundamental theories of physics seem to rely on local symmetries, and this list includes both gauge theories and gravity. And there is an obvious big why in this context. There is a hint, at least coming from gauge theories, if one uses the weak coupling intuition, that without non-trivial vectors with gauge symmetries, we cannot construct UV complete theories. This is something we learned in the context of weakly coupled theories in our QFT class. However, there are many holes in this hint because the UV can be strongly coupled, the UV may not be even a quantum field theory, etc. Long time ago, Holger Nielsen tried to argue that the gauge theories are generic low energy artifacts of non-gauge high energy quantum field theories. But despite some work that has been done in this area, it is not known today whether such a statement can be true in general. The other known interaction, which is gravity, has also local invariance, but it's of quite a different form. The underlying invariance, which is the diffeomorphism invariance, is, however, not unique to gravity. There are many quantum field theories that can be diffeomorphism invariant without a fundamental graviton field. And a common example you all know is Nabucco theory. Now, our two main frameworks in physics, on one side quantum field theory and on the other side gravity, although each one of them is very successful in its own domain, as also you know, clash when they make predictions in overlapping contexts. And the first such context is the cosmological constant problem. The QFT predicts a generically large vacuum energy, while the one we see through the filter of gravity is tiny. The other clash is the black hole information paradox, albeit so far this is theoretical. Now, most experts believe that the weak link in these is gravity, and many efforts have gone in modifying gravity in different ways. All such efforts have shown that the task is extremely difficult, and the fine-tuning seems to be the norm in this context. There are others who believe that the problems exist because we do not fully understand the quantum theory of gravity. Now, some naive thinking suggests that this should be operational near the Planck scale, but this argument also has several holes. The most important hole is that gravity, being a bosonic theory, is highly sensitive not only to large momentum transfers, but to strong gravitational backgrounds that create new large scales in the problem. And a related question in this context is, what are the short distance degrees of freedom in gravitational physics? This seems to be crucial for the black hole paradox, and it may be probably relevant for the cosmological constant problem. As you also know, unlike gauge theories, gravity as an infrared theory is non-normalizable. And after efforts that span more than 50 years, the only examples of a quantized gravitational theory with a semi-classical limit are those that are included in the framework of string theory. Now, the type of quantization of gravity that string theory gives us comes at a cost, and the cost includes an infinite number of additional degrees of freedom and a new scale below the Planck scale, which is the string scale. Many people believe that string theory provides a UV complete theory of quantum gravity. However, this is false. Perturbative string theory, as we understand it, provides a consistent cutoff theory of quantum gravity, and the cutoff is the Planck scale. Perturbative string theory cannot answer questions that involve transfers of energy at or beyond the Planck scale. In the past, there have been many attempts to capitalize on a winning strategy, which is resolving non-normalizable interactions. And this has worked several times, and two famous and very distinct examples are the weak interactions and the strong interactions. An example I will use here as a good example is the low energy theory of the strong interactions. It is infrared free, and it's non-normalizable. It's the theory of pions, essentially. And it reminds us quite well the problems with quantizing gravity. In that theory, it was eventually understood that one can quantize the low energy degrees of freedom, which are the pions in the chiral Lagrangian, but this description has a cutoff. Practically, it's about 1 GeV, and it needs a large number of counterterms. On the other hand, the high energy degrees of freedom in this context, which are the quarks and gluons, are different from the low energy degrees of freedom, and the quantum field theory associated with them is a UV complete gauge theory, that is QCD, which is effectively strongly coupled in the infrared. Now, if one takes this as a clue, this would suggest that the non-normalizability of the graviton appears because of its compositeness. That is, the graviton is a low energy bound state. Now, this idea is very old, and many attempts were made in the past to construct gravity theories where the graviton is a composite field made out of more elementary fields of all types, scalars, fermions, vectors, etc. But all such attempts fail to go beyond the classical and to provide a dynamical explanation of why the bound state appears featureless at low energies. And in this context, in fact, the Weinberg-Witten theorem was proposed, which assumes Lorentz invariance and a conserved Lorentz covariant energy momentum tensor, and then proceeds to prove that no massless particle with spin S bigger than 1 can couple to the stress tensor, and no massless particle with S bigger than 1/2 to a global conserved current. Now, this seems, of course, very strong. However, it has loopholes because it does not rule out, for example, a theory that contains a fundamental massless graviton. The loophole in this case is that in the presence of a fundamental graviton, the stress tensor is not conserved in the presence of a metric. And moreover, in fact, it's covariantly conserved. And moreover, the projection on helicity 2 is a non-covariant description, has a non-covariant description in general metric. But there are also other ways of avoiding this theorem. In the case of massless vectors, for example, the statement says that no massless, non-abelian vectors can couple to a conserved Lorentz covariant global current. And therefore, it would seem that Yang-Mills theory is excluded. However, as you all know, this is avoided, and standard non-abelian gauge theories exist because the conserved current is not Lorentz covariant. It's Lorentz covariant up to a gauge transformation. There are even more interesting counterexamples to this theorem. For example, it is known through the work of Komagosky that at the lower end of the conformal window is in n equal 1 super QCD, the rho mesons, which are composite fields, become massless, but at the same time develop a gauge invariance. And these are essentially the magnetic gauge bosons of Seiberg. Their effective theory is renormalizable, being a standard non-abelian gauge theory. The final caveat is that Lorentz invariance is crucial. Otherwise, the notion of masslessness is not well defined. Even in spaces with a large symmetry like the sitter and the sitter, this notion changes. So the conclusion is that the Witten-Weimar theorem can be invaded, but it is a serious litmus test for all emergent graviton theories. What we will see in the sequel is that although the essence of the Witten-Weinberg theorem remains true, the effective theories for composite gravitons can be very rich. If one would like to implement this idea, the natural state that could play the role of the emergent graviton is, of course, the state that's generated out of the vacuum by the energy momentum tensor. It has the proper quantum numbers of the graviton, and it is transverse because of energy conservation. Now, if you look at what this state is in weakly coupled theories, this is a spin 2 multiparticle state, and therefore its interactions are expected to be non-local. If, on the other hand, the interactions are strong and make this state a true tightly bound state, let's say that it has a size L, then maybe one can hope that one can reproduce an effective gravity associated to it at scales which are much larger than this size L. In particular, in the limit of infinitely strong interactions, we would expect to obtain a good point-like interaction theory for this bound state graviton. Of course, the Witten-Weiberg theorem constrains such bound states, but we will come later to such constraints. Now, it is important to remember that in the presence of a strong attractive interaction in the spin 2 channel, then may be, generically speaking, a tower of states that are generated by the energy momentum tensor acting on the vacuum. If the theory, the associated theory, is not conformal, such a spectrum typically is discrete, and it would be associated generically with the complex poles of the two-point function of the stress tensor. And again, generically speaking, many such states will be unstable. If, on the other hand, the theory is conformal, such states will form a continuum. And this is precisely the case in ADS-CFT. The main paradigm, in fact, that we have, the new, if you wish, version of the composite graviton paradigm that we have now is coming from the ADS-CFT paradigm. ADS-CFT relates quantum field theory to string theory, and therefore to a theory of quantum gravity. Of course, that the gauge theory at large n can be described by weakly coupled string theory was anticipated long time ago since the work of 't Hooft. The emergent dimensions are the avatar of the large n limit. The eigenvalue distributions become continuous extra dimensions, as it was already seen in simpler matrix models. However, it's still a puzzle why the higher dimensional theory has diffeomorphism invariance. The masslessness of the higher dimensional graviton, as we understand it now, is related to the energy conservation of the dual quantum field theory. The holographic duality essentially implements what we discussed already about the graviton, and in general also about other bulk fields. They are composites of generalized gluons. The strong coupling in quantum field theory and the higher dimensionality, as expected, are important in making the gravitational theory local by suppressing the string corrections. And the other important ingredient is the large n limit. It makes the bulk fields, which are composites, interact weakly, despite the fact that the constituents interact strongly. So what we learned from the ADS-CFT paradigm is that strong coupling in quantum field theory makes gravitons tightly bound states, large n makes gravitons weakly interacting, and both of the above give an effective semi-classical theory of composite quantum gravity. We do believe today that this duality can be used to define string theory and gravity non-perturbatively by using the quantum field theory to define the physics beyond the obvious cutoff of string theory. Of course, to show that, one needs to essentially understand why ADS-CFT works. Let me start by trying to become more quantitative and see how I can describe the dynamical theory of the emergent metric, which is associated to the vacuum expectation value of the stress tensor of a quantum field theory. So to implement this idea, I will have to construct a theory that describes the dynamic of such a graviton in a quantum field theory. And as a warm-up, I can consider a translation invariant QFT at a fixed background metric that I call G-ball, mu, and I will add a scalar source to have something else also beyond that metric, which is coupled to some scalar operator O. This is for purposes of illustration. The presence of an arbitrary background metric in the quantum field theory in general, of course, breaks translational invariance, but as we all know, if you redefine derivatives to covariant derivatives, you restore energy momentum conservation in the absence, of course, of other non-constant sources. the expectation value of the stress energy momentum tensor is given by the variational derivative of the action with respect to the background metric, as usual, etc., etc. Now, the key element to start in order to describe the physics of the emergent graviton is the Zwinger functional, which we define it, as usual, as the generating functional of the correlation functions of the energy momentum tensor and, in general, other sources. And I have written it here schematically, where phi are the quantum fields of the theory, g mu nu is a background metric, which is fixed, it's a source, and j is another scalar source. Now, to make this finite, of course, and to have the right properties, first of all, one would have to assume the presence of a cutoff that preserves the diffeomorphism invariance so that these quantities eventually can be made finite. Of course, for whoever has thought about this, this is tricky business. But for the moment, we can have dim reg in mind because I don't want to delve too much into it. The other question is to what extent this W, G, and J is unique modular normalization and the usual renormalization ambiguities at the linearized level. And as we know, in general, it is not because of what is known as improvements. There are also ambiguities at the nonlinear level because one can add, in general, diff invariant functionals of the curvature. All of these, in fact, functionals correspond to what are known as improvements of the stress tensor, sort of what you couple, if you wish, to the background metric. And both exist at linear and nonlinear level. This is, in general, what I can call the scheme dependence of the Zwinger functional. But once you fix the scheme dependence, then the Zwinger functional is finite, and diffeomorphism invariant in the standard case. If you transform all the sources, including the metric, in the usual way at the general coordinate transformations, then it is invariant. Now, if I take the background metric to be my fixed fiducial metric, for the rest of the talk, the fixed fiducial metric will be the Minkowski metric, plus a perturbation, then the Zwinger functional as a function of this perturbation encodes essentially the interaction energy between energy momentum sources. That's what H is. And in this case, the expectation value of the energy momentum tensor, H, which in fact, this is unfortunate, it's different from this H, but this, we will forget it for a moment. So H is here defined as the expectation value of the energy momentum tensor, and it's given by the standard derivative of the Zwinger functional. And then I can do the standard Legendre transform to define the effective action for the metric. There is a tiny modification here because I subtract my fiducial metric, but otherwise, this is the standard Legendre transform with respect to G, H times G minus W. From the properties of the Legendre transform, we know that gamma is the generating functional of the 1pi energy momentum tensor correlations, that it is extremal, that is, if you vary gamma with respect to H, and you set in the end the background metric to be your fiducial metric, then this is vanishing. And if you evaluate it in a solution of this, I can call it an equation of motion, then I recover the original Zwinger functional in the fiducial metric. And this type of equations, in fact, are essentially, can be thought of as the equations of dynamical gravity, where essentially, and this being the effective action, where essentially the dynamical metric is almost, and I will see why later, the energy momentum tensor vacuum expectation value H mu nu. All the other sources you might have in this description, like J, for example, represent energy momentum carrying sources. This description is diffeomorphism invariant by construction. The related theory is a bigravity because it involves a dynamical metric H and a fixed fiducial metric G bold, which is the metric on which the original quantum field theory was defined. The interactions that are mediated by this graviton are essentially summarizing the exchanges of the energy momentum tensor as we postulated. The emergent graviton propagator one would compute from the effective action by construction is generated by the poles of the energy momentum tensor 2-point function in the original theory. And to see in more detail what the effective interaction looks like, let me write first of all the interaction energy in the Zwinger functional at quadratic order in the perturbation, which is h, 2-point function of the stress tensor times h. And then substitute the general form of a 2-point function in a translationally invariant quantum field theory. This is written here. It has several pieces. There is a constant piece which exists because of the translation word identities if the stress tensor has a non-zero 1-point function. And V is the coefficient of the 1-point function, which is written here for the Minkowski metric. Then there are two pieces. There is a spin 2 piece and the spin 0 piece. And they contain, of course, the usual projections to conserved quantities that you all have seen. And they're multiplied by momentum functions, which are, in fact, in general, written in terms of spectral densities in the standard ways, that up to a certain coefficient, which is conventional, and the power k to the 4, it's a sum over spectral functions with the usual, of course, scalar propagator. And this you can write both for the spin 2 and the spin 0 spectral density. So this is generically what you substitute here to see what is the interaction of sources. Now, I should discuss a few contact terms in this 2-point correlator because they are important eventually for the physics. There is, first of all, a contact term at order k to the 0, and this is fixed by the translational word identity. It's basically this term. Then there are two more terms. One appears at order k square. A4 here is a numerical coefficient, which is not important. K square is here, and then the usual projections of spin 2 and spin 0, and then two coefficients that I call delta 2 and delta 0. And for infrared regularity, these are not independent. They must satisfy this constraint. And then you have an extra contact term at order k to the 4th. This is scheme dependent, comes from normalization, and it has, again, a similar form, now multiplied by k4. This shouldn't be there, by the way, it's a mistake. Now, if you include these contact terms, the interaction that's mediated by the state associated with the stress tensor at the quadratic level, by substituting, in fact, in this formula, this answer, you get the non-contact term part of the spin 2 spectral function with this combination of the sources. And if you note the 1/3 here, this is the associated combination of sources that is associated with the interaction due to a massive graviton. And another contribution, which has to do with the trace of the metric. H is a trace of the metric with respect to the Minkowski, using the Minkowski metric, and the associated spectral density for spin 0. Now, these now start at higher order. B2 starts at order k to the 6th for small momenta, and B0 starts with the anomaly term k to the 4th log k. Now, this interaction depends crucially on the structure of the spectral densities. If, for example, you have isolated poles and you go near a pole, then the spectral density, either of spin 0 or spin 2, will have some residue times the usual type of pole. And if you keep track of dimensions, the residue has dimension 6, mass dimension 6, because B has dimension 4. The resulting interaction involves a massive spin 2 particle of mass m2 in this particular case, and a massive spin 0 particle of mass m0. In a unitary theory, all the residues are positive, and the exchanges are never ghost-like. And if you do an appropriate rescaling of the interacting densities, you can find what is the associated Planck scale, which is associated to this interaction. And this is given, in fact, by the 1-point function of the stress tensor square divided by this residue. And the associated field theory that you get from this is essentially by gravity theory. It has a fluctuating metric, which is the emergent metric, and it has a fixed fiducial metric, which is the metric on which you defined your original quantum field theory. So this is basically giving you an idea how the emergent metric sort of emerges and behaves in a single quantum field theory. And now, if you want to go one step further and see to what extent the metric we see in our realistic theory, the standard model, is of this form, then you will have to ask the question where such an emergent metric can come. It clearly cannot come from the standard model because it wouldn't have the properties that we want. So it has to come from a different sector, some hidden sector, some other theory that is coupled to the standard model. So in a sense, what we want to do is to take this proof of principle that I showed you before and try to implement it in a theory that involves, let's say, the standard model. Now, what we have seen so far is that we have the full nonlinear diffeomorphism variance, we have a dynamical gravity, and in this way, what we would expect is that the type of semi-classical gravity we observe will come from a theory who is a holographic theory and has also a dual description as a higher dimensional gravitational theory. Now, in ADS-CFT, which is eventually the type of situation that we would like to address, the background quantum field theory metric, which, as we said, appears in the effective theory, appears in a more subtle way. It appears as a boundary condition instead of appearing explicitly in the equation. And the theory essentially in ADS-CFT becomes from bigravity in 4 dimensions, a standard gravitational theory in 5 dimensions, but with non-trivial Dirichlet boundary condition at the NDS boundary. But as I said, what we now would like to do is to have the graviton come from a hidden theory, and therefore to describe it as an emergent degree of freedom. So we need a hidden sector. This hidden sector should be coupled to the standard model at some high scale, and only a few interactions will survive in the infrared between the two theories, as all or most of the interactions would be infrared irrelevant. And in fact, this situation will match the infrared freedom and the non-renormalizability of gravity. Now, we also have seen that if we want this graviton to be tightly bound and weakly coupled, then this hidden sector theory must be a large N, strongly coupled, therefore probably holographic quantum field theory. And we are therefore led to couple a large N theory to the standard model in a UV complete fashion. In order to do that, we need to postulate that this theory is coupled to the standard model by some set of bifundamentals that we call the messengers. These messengers will have a mass that we will assume to be much larger than the typical scales of the visible theory and that of the hidden theory. And below this mass scale M, we can integrate out the bifundamentals to generate contact interactions between the operators of the hidden theory and that of the visible theory.
Professor Kiritsis, your full screen has come down, so you can maybe full screen.
Just a minute. Okay. So let me consider the coupling of this hidden theory to the visible theory by a coupling of their stress and energy momentum tensors. So I have a coupling of T mu nu, that's the visible or standard model energy momentum tensor, to the hidden one. The hat indicates the hidden theory. And another coupling that couples their traces in the fiducial metric, which I will take to be the Minkowski metric. And this is defined at the cutoff scale, which is the messenger scale M. And lambda prime are irrelevant couplings with dimension mass to the -4, and typically they will have a size which is 1 over m to the 4th. Now, to simplify the form of this, let me define this script C to be the ratio of these couplings, redefine the observable energy momentum tensor by absorbing C times the trace, and therefore I can rewrite this as a single coupling like this in terms of T bold. And the first thing you can notice in this context is that the expectation value of the hidden energy momentum tensor plays the role of an emergent metric for the visible theory, as we have anticipated. Now, I can do a calculation, and I can do this calculation up to lambda square, and this is typically a good approximation of what I will obtain from this interaction by integrating out the hidden theory. And I will get a new effective interaction, which has a linear piece, and the linear piece is proportional to the expectation value of the hidden energy momentum tensor, which I called lambda hat. And then it will have a quadratic piece in the observable stress tensor, which it will be essentially coupled by the 2-point function of the hidden energy momentum tensor. And I rewrite this same term here in momentum space. And the obvious result is that now I have introduced a new interaction between energy momentum sources in the visible theory because of the exchanges of the energy momentum tensor of the hidden theory. Now I can reformulate this interaction by integrating in a classical spin-2 field, which I call again H mu. And if I do this, I get a quadratic term where this tensor now is the inverse of the 2-point function, and I get also a linear coupling to the observable stress tensor. Now, it remains to examine under what circumstances this inverse 2-point function is well defined and what tensor structures it involves. Let me again assume that the hidden theory is a Lorentz invariant quantum field theory in flat space. And then, as we have seen, the connected 2-point function contains a constant contact term because of the diffeomorphism word identities and because the expectation value of the 1-point function is not zero. And then the usual two pieces that are associated with the various projection operators for spin 2 and spin 0. Let me now try to analyze this at low momenta. So I'll take k to 0. And then these functions b and c, in fact, start at order k square and with a coefficient that is related. And in fact, this is specified by the diffeomorphism word identities. So B0 hat is a dimension 2 parameter. So I have two parameters essentially at order k square, lambda hat, the 1-point function, and B0 hat. On the other hand, if lambda hat here is 0, then it is well known that this is conserved, and therefore there are 0 modes, and therefore you cannot invert the 2-point function. In this case, if you need to invert and describe an emergent graviton, you have to do it to the space orthogonal to the 0 modes, and this will give rise to an effective non-local theory for the graviton. Now, if you do the inversion, you can find this result. It has a constant piece here, which is controlled by the 1-point function, and it has also a piece quadratic in momenta, which has this particular structure. Now, for those of you who have looked at linearized Einstein tensors, you will realize that this is not exactly what you get in gravity. However, if you do some redefinitions, and here I define a new field, which is script h mu nu in this particular way. This involves a certain rotation and also a constant shift. And h here is the standard trace with respect to eta mu nu. But I also redefine the visible energy momentum tensor by a constant shift. And in this case, by using this, I can rewrite the effective interaction I derived in this form. This contains an Einstein term and a cosmological constant at quadratic level. That is, I write the metric as eta mu nu plus this script h, and a linearized coupling to the energy momentum tensor. And it contains these two parameters. One is an effective Planck scale, and the other is an effective cosmological constant, which you can connect to the 1-point function of the hidden stress tensor and this scale b hat 0 that appears in the 2-point function in this particular way. You see also that if you want the Planck scale to be Planck scale square to be positive, b hat 0 should be negative. So this seems to be the case in simple quantum field theories, but we have no general proof. Now, if I look at the second term, which describes the coupling of the visible quantum field theory to the emergent graviton, this combination, in fact, can be written as in this form, expanded around flat space. And moreover, this energy momentum tensor, which is the visible one, involves a non-trivial shift of the energy due to the coupling of the two theories. Now, I will call this dark energy in quote marks without implying that this is the usual dark energy we're discussing, but it's some kind of energy that comes from the existence of the hidden theory. Now, this exists as we have seen, and it is because of this dark energy that one can show that the flat fiducial metric is always a solution to the equations of this emergent gravity. Now, we can use this description to compute the non-contact part of the induced interaction between standard model sources without expanding in momentum. And in this case, we get a formula that is similar to the case of a single theory. It contains a spin 2 contribution, which is of the form, again, which is coming when you exchange massive gravitons. It's multiplied by the spin 2 spectral density of the hidden theory. And it contains another contribution, which is a scalar exchange. This comes from the trace. And it has a coefficient that is related to this constant C that I remind you is part of the original interaction or coupling between the two theories. Now, there is a special value here for which the scalar interaction decouples. And it turns out that this constant C, this particular value, if we were in 2 dimensions, it would be the same as was found to be integrable and gave rise to the usual TT deformations of conformal field theories. And in dimension 4, as Marika Taylor had shown, this is also the special value that has similar properties as the one in 2 dimensions. The other thing one can observe from this formula at the quadratic level is that the interaction is always attractive because the spectral densities are positive, and stable because the masses are non-negative. The associated masses are non-negative. For example, if I again go next to a pole, an isolated pole of the spectral density, and which is at mass, let me call it M2, and I calculate the effective Planck scale, it is given by the messenger scale to the 8th divided by the residue. And if I take the residue to be of order the position of the pole, then it is saying that the Planck scale is a factor, which is m over m2, that typically is larger than 1. And therefore, this indicates that the effective Planck scale is, in general, much bigger than the messenger scale. Now, this description, in general, can be extended by a fully nonlinear description, and one can write, at least formally, using the techniques of the effective action, what is the full nonlinear action that controls the dynamics of now the coupled theory. Of course, to calculate that explicitly, at least in some limit, is not always possible. What we have done here is to calculate it either in the derivative expansion or in the exchange expansion that is at quadratic order in effective gravitons. Let me end, in fact, by some comments and open ends. In general, of course, you can integrate in many other fields. I only did it for the graviton. However, in general, most of them will have large masses of order the messenger scale. And generically, again, without fine-tuning, you would expect that the only protected ones are, apart from the graviton, the universal axion, which is associated with the instanton density of the hidden theory, and global conserved currents that would appear from the point of view of the visible theory as graviphotons. It is not yet clear how to bridge the ultimate infrared nonlinear theory with one of the massive graviton theories. We have seen that if we expand in momenta, we get a theory that seems to be a theory with a kind of dark energy, but also a cosmological constant. But on the other hand, generically, especially if the hidden theory has a discrete spectrum for the stress tensor, we expect that at least near the poles, we have a description of a massive graviton theory. And there people have derived some types of actions that describe them, but so far we do not know how to connect the two. In general, one can show that in all emergent graviton theories, after including all quantum corrections, the background fiducial metric on which you define your original quantum field theory is always a solution. Therefore, you can interpret this as there is no standard cosmological constant problem. As I said, there is a kind of dark energy that comes always from the hidden theory. In general, you can have additional sources in the hidden theory that may provide new sources of quote unquote dark components like energy, matter, etc. Now, when the hidden theory is a holographic quantum field theory, then the description I presented here, in fact, transforms into a brain in bulk or brain world description, which has been discussed in the past, but with Neumann boundary conditions at the ADS boundary. In fact, in this case, as we showed recently, one can self-tune the cosmological constant and always obtain a massive graviton on the brain from the DGP pole with a mass which scales as 1 over n, where n is the n of the large n hidden theory. Now, if to this description, if one adds the natural bulk axion that exists always, then in principle, one can also correlate the self-tuning of the brain cosmological constant to a solution of the hierarchy problem along the lines that have been discussed in a somewhat different context using the relaxion idea. As you have seen, there is always a scalar mode, which I will call the dilaton, and there are more than one reasons to call it the dilaton, which appears always together with the spin 2 graviton, which comes from the trace of the energy momentum tensor. This is always positive, as I showed you in a unitary quantum field theory. This, for example, is negative if you try to use a massive gravity theory without Pauli fields tuning, which is the tuning that decouples it completely. This can be a natural dark matter or dark energy candidate, in fact. However, the most difficult problem first to solve is that the existence of a light such particle that can compete, if you wish, with a graviton is a major problem for the principle of equivalence, which is precisely also the problem we have with the dilaton in string theory. Now, it is not known yet if there is a hidden theory that will give an emergent graviton theory that is in agreement with data, because we have many constraints for this, and we don't know enough about the structure of the energy momentum spectra in quantum field theory. However, bootstrap techniques might answer the question whether the spectral properties of the energy momentum tensor that we need can appear in a quantum field theory. One can try to think of black holes, but black holes depend on nonlinear dynamics. There is a certain puzzle here even before you study this, because on one hand, from standard gravity theories that people have studied, one cannot find static black hole solutions. On the other hand, in holographic contexts on which we have a brain in the bulk, since the time of Randall and Sundrum, people tried, in fact, to find static black holes. It took, in fact, over a decade to do that, but now we know that such black holes exist and they are static. It is not known why these two things seem to not agree. And the bigger problem, in fact, in this context is we do not have a reliable, so far, nonlinear theory in which to address this question in the context of at least some theories of emergent gravity. It is also interesting to realize from the way I described emergent gravity that even the signature of the metric, of the emergent metric, can change. For example, as we have seen, the metric is the expectation value of, let's say, the hidden stress tensor. If the hidden theory is close to its ground state, then we know that the stress tensor is close to the Minkowski metric, and therefore the signature is Minkowski. However, if the hidden theory had a stress tensor, which was, let's say, cosmological of a photonic type, then we know that the stress tensor has Euclidean signature. From this, one can conclude that if the hidden theory is near the ground state, then the signature will be Minkowski. But if the hidden theory is in an excited state, then the emergent metric will become of Euclidean signature. And I don't know what this would mean in terms of somebody who's in the standard model and observes this. And with this, I would like to end and thank you for your attention.
Thank you very much, Professor Kiritsis, for a very wonderful and very interesting talk. So are there any questions or comments?
Yes. Can I ask a question?
Yes.
Yes. Hi.
Hi, Costa.
What do you do with the VDVZ discontinuity of massive gravity? Maybe I missed it. If your graviton is massive, this won't be in agreement with experiment, no?
That's correct, and this is a problem. I haven't mentioned it, first of all, so you haven't missed it. This is a problem, of course, that exists in all theories in which the graviton is not massless. And here, as you've seen, always the combination of the sources is that of massive gravity. Therefore, there is generically a VDVZ discontinuity. But this issue has been discussed in the past because people have discussed this issue in other contexts, and the most complete discussion in terms of experimental constraints on experimental data comes, in fact, from discussions from the DGP setup. So what is the outcome? First of all, unless you have a nonlinear theory, you don't know where is the analog of the Weinstein scale. And the Weinstein scale is the scale which separates the regime in which the scalar mode of the massive graviton is strongly coupled and decoupled, and therefore does not appear in the interaction of sources, and the regime in which linearized gravity is correct, that is the one I showed you, which shows the massive tensor, and therefore you have a VDVZ problem. At the time, Valley and collaborators have shown that one can choose numbers, if you could choose freely, let's say parameters, that one can make it compatible with today's data, but it's roughly at the border. But here, of course, this is an important problem eventually to be understood, together also with masses. I mean, you have to find a theory which has a mass for the graviton which is sufficiently small, that other masses above, are sufficiently high, as you know, that the spin zero mode is not bothering you with problems of the equivalence principle. And on top of that, of course, at the nonlinear level, the VDVZ discontinuity. There is no-go so far, but in order to make any statement, one should have a nonlinear theory and then start looking at models. That's all I can say now.
Thank you very much.
Okay, other questions and comments?
Hi. So on page 12, you have a formula that shows that the C equals minus 1/3. You don't have the last term in that expression, and the resulting deformation is like the TT deformation in 4 dimensions of this Marika-Taylor's.
Here you mean? Yes.
Yes, right. So it's known that the spectrum in that case is non-unitary in that when C equals 1/3 for minus 1/3, for example. How does that play a role in the discussion that you just?
You're talking about the spectrum of the complete theory?
Yes.
In 2 or in higher dimensions?
In higher dimensions as well, the spectrum is non-unitary, right? The higher energy states becomes imaginary.
I don't know. In fact, let me put it like this. This description is at the quadratic level with a fixed interaction. Now, if you include the complete UV interaction, which will include many other terms, then eventually it will be unitary. So the problem, and that's why, in fact, I do not think that tuning the spin zero modes to go precisely to this limit is a solution of the equivalence principle problem. This will be corrected by higher interactions. Therefore, although I know that if you construct this theory from a UV complete theory, it will be okay. In that case, it would mean that you will have also other contributions in the interacting theory that will make the total theory unitary.
Okay, I see. So you are saying that you are not supposed, you cannot trust the theories at very high energies, but at low energies you still have real spectrum. There, everything will work fine.
What I expect, if you wish, is that if I work below the cutoff, normally the non-unitarity will have to appear above the cutoff. Now, if you give me more information, or maybe we should discuss offline, we can check at what energy scale the non-unitarity appears. And that would be, in a sense, also the scale where this theory has to be fixed.
Okay, I understand. Okay, thank you.
Okay, other questions?
I would like to ask Jyotirmay.
Yes, Aranta, please.
Thanks, Elias, for this beautiful talk. And actually, I have a question that Yeah, so in our setup, when we have a similar kind of couplings using two effective metrics. And there what we see is that if you have some emergent metric of some kind, well, ours is not really an emergent metric. It's simply an artifact of the coupling. But then in this, if you have some emergent metric, you have to worry perhaps that could be causality violation, because the light cone of the emergent metric could be kind of wider than the actual background metric light cone. So there has to be somehow, you have to define the causality with respect to the actual background physical metric or somehow, or that is, so I would like to, maybe it's a naive question, just asking how to pose questions about causality here.
Answer in this particular case, but I have an answer in the case of a holographic theory. And I think, I haven't thought of that, of course. I think that can be extended also in this case. In a holographic theory, as you know, you have a bulk metric, so there also you can have causality violations on slices. But there we know, in fact, that causality is not violated because of the usual constraints, null, integrated null energy condition, etc. And therefore, whenever you always travel through the bulk, you always put more time than when you travel along the slice. I think something similar should happen here, but I haven't thought of it, but I suspect it can be shown. I will think about that.
Thank you. Thank you.
All right. Any other quick question? We are already running slightly late, I think. But if there is one more quick question, we can take it. All right. If not, let's thank Professor Kiritsis once more for a very beautiful talk.
Thank you very much.
Yeah, thank you. So Dr. Meyer